Okay. So the last speaker of the conference is Donghyun Kim from Sungkyunkwan University, and he's going to talk about McDonald polynomials, Butler's conjecture, and science fiction. Let's welcome the speaker.
Okay, thanks a lot for the introduction. Thanks for the invitation. I'm very glad to be the last speaker of this conference. As a closer, I'll present the joint work with two organizers. The first organizer, Seungjin Lee from Seoul National University, and the second organizer, Jae-sung Oh from KIAS. And please feel free to interrupt during the talk if I'm too fast, if something is unclear, or if you have an objection on what I said. First, here is the table of content. I'll define the basic notations and conventions we'll use throughout this talk and give a short introduction to McDonald polynomials. Then I'll discuss what happens if we plug in t equals q to the k to McDonald polynomials. After that, I'll tell you about Butler's conjecture and science fiction conjecture. If time permits, I'll say about our discoveries of Qt Catalan numbers and Krabberas numbers in science fiction conjecture. Okay, so basic definitions and notations. Partition is a weakly decreasing sequence of positive integers. And to denote corresponding Young diagram, we'll use the French notation instead of the English notation. And here you see the example. And we'll index each cell of the Young diagram with natural Cartesian coordinates. Now let's move on to McDonald polynomials. I'll assume that everyone in the audience likes McDonald polynomials. Many speakers prior to me gave beautiful talks about McDonald polynomials. So at this moment, you might feel pretty familiar with McDonald polynomials. I'll introduce McDonald polynomials in a very concise way. These are all you need to know about McDonald polynomials to enjoy the talk today. Okay, first, it is a symmetric function with Qt coefficients. The example shows McDonald polynomials for the partition 2, 1 expanded in terms of Schur basis. As you can see, there is a Schur positivity. And to prove Schur positivity, in 90s, Garcia and Heyman constructed a candidate bigraded module, whose graded Frobenius characteristic is a McDonald polynomial. And later, Hyman proved it, settling the Schur positivity. I will not give a precise description of Garcia-Heyman module. It lives in an ambient space, SN module that is a polynomial ring with two sets of variables, x and y's. And the SN action is given by a diagonal action, permitting each variable set simultaneously. And the elementary fact is that if we plug in q equals t equals 1 to McDonald polynomial, then it becomes very simple. It does not depend on the shape of the partition, but it only depends on the size of the partition. Okay, now let's see what happens if we plug in t equals q to the k to McDonald polynomials. The start of our project was to answer the following question. If you give me two different partitions, then they will obviously give different McDonald polynomials. But if we specialize t equals q to the k, for some cases, different partitions gave the same McDonald polynomials. For example, when t equals q squared, McDonald polynomials for the partition 4 and partition 2, 2 were the same. And if we set t equals q cubed, then McDonald polynomials for the partition 4 and 3, 1 were the same. And actually, this question was answered in the paper Platistic Formulas for McDonald Qt coefficients by Garcia and Tessler, a paper written in 90s. And the answer is quite elegant. We consider the k-filling of the partition. So the rule is we fill the number on each box. And if we move horizontally, the number increases by 1. And if we move vertically, then number increases by k. Okay, this is the example. The one-row partitions has only horizontal moves. So we fill the number 1, 2, 3, 4. And for the partition 2, 2, the first row has number 1 and 2. And the second row has numbers 3 and 4. It's because the vertical move increases the number by 2. And you can perform the similar thing to the picture on the right. And the answer for this question is here. So if lambda and mu have the same k-filling, their Macdonald polynomials are the same when t equals q to the k. So these two pictures explain the identities, these two identities in the previous page. Okay, now let's move on to a more specific situation. Assume mu is obtained from lambda by moving one cell to the right above the row. In the picture, red cell is such cell. And let's say that the horizontal distance that the red cell moved is k. Then from the k-filling criterion in the previous page, we can see that the Macdonald polynomials for lambda and Macdonald polynomials for partition mu becomes the same if we specialize t equals q to the k. It is because if we write the k-filling, then the numbers on the red cell here and the red cell here, they will have the same numbers. And this identity implies that t minus q to the k divides h tilde lambda minus h tilde mu. Now I'll tell you our first goal today. We want to understand this quotient. So the polynomiality of this is guaranteed by the logic here. Or we can also study this twisted quotient. And okay, someone might complain, we are moving a cell one row above, and this condition seems too restricted. So let's remove that restriction. We'll freely move a single cell, say vertically above by A and horizontally left by K. Then we have to modify T powers appropriately. And we don't need to study both of them. We don't need to study both because it is enough to study one of them. Once you understand one, then you automatically understand the other one. So I will choose the second one for our target. And someone might ask if there is a reason for studying this. To answer that question, we need to go back to 90s and explore Butler's conjecture and science fiction conjecture. Before going further, I will define a notation, capital T lambda, as follows. So for each cell I, j in the partition, we product over q to the I and t to the j. And this is the example. And this capital T lambda is not something new. It appeared in previous talks as an eigenvalue of Nabila operator. Now I'll give you a quick quiz. Let's get back to our situation. Mu is obtained from lambda by moving a single cell, and the distance and the vertical distance is A and the horizontal distance is K. Then what is the ratio between capital T lambda and capital mu? Well, I can wait 5 seconds. Okay, so
T to the A, they differ by T to the A and Q to the K.
Oh, great. Yeah. So the answer is Q to the K to T to the A. And remember that our goal was to study this guy. So it makes no difference if we replace this guy with capital T lambda and capital T mu. And I prefer this description because it gives a picture-free description of the one that we want to understand. And now it's time to answer this question. Why do we need to study this? And I'll start by giving a motivating example for Butler's conjecture. Consider lambda equals 2,2 and mu equals 2,1,1. Note that these two are different by a single cell, which is the situation we want to study. And here are the sure expansions for two McDonald polynomials, for lambda and mu. And yellow monomials are the term that appear in both McDonald polynomials. And the light blue monomials are the terms that appear with the ratio exactly q to the t. So here qt and t square, the ratio is q to the t. And here q square and qt, the ratio is q to the t. And if you look at here, q square t square and qt cube, and the ratio is q to the t. And this means that there exist a sure positive polynomials a and b satisfying the following equations. In our case, a will be the collection of yellow terms in the previous page, and b will be the collection of light blue terms. Now imagine you solve linear equations with variable a and b, then you'll get these two. These two are sure positive. In 90s, Butler conjectured that if lambda and mu are different by a single cell, then these two guys are sure positive. So the one that we want to study, this one, left one, was conjectured to be sure positive quite long ago. Now I'll discuss science fiction conjecture and how it is related to Butler's conjecture. In late 90s, Bergeron and Garcia wrote the paper, Science Fiction and McDonald Polynomials. So the setting is, assume lambda has k removable corners and let lambda superscript 1 to lambda superscript k be the partitions obtained by deleting these removable corners. For example, let's say lambda is the partition 4, 3,1,1. And as you can see in the picture, this partition has 3 removable corners. And it has, so there will be 3 partitions obtained by removing one of them. Capital lambda superscript 1 to lambda superscript 3. In their paper, Bergeron and Garcia conjectured that Garcia-Heyman modules for the partitions lambda superscript 1 to lambda superscript k are related nicely. I want to explain precisely the description for the nicely, and in terms are related nicely in terms of the operation flip. Roughly speaking, flip operation on the module side corresponds to the omega involution plus bigrading reversal on symmetric function side. For example, in the two-corner case, we have 2 Garcia-Heyman modules. And we draw the Venn diagram. And let's denote each region by A, B1, and B2. Then the science fiction conjecture implies that B1 and B2 are isomorphic to flip of the module A with a suitable bigrading scalar. So we have the following 2 equations, and once we solve for Frobenius of A, we get this identity. Again, this identity is conjectural, as it is built upon science fiction conjecture. And here's the summary of the science fiction conjecture. Assuming the science fiction conjecture, we can express the Frobenius characteristic of intersections of Garcia-Heyman modules as a linear combination of corresponding McDonald's polynomials. And the example in the previous page has done that for the intersection of two Garcia-Heyman modules. We can see that science fiction conjecture implies Butler's conjecture, because Butler's conjecture is to prove the sure positivity of this one, and science fiction conjecture suggests the candidate module. So I believe this gave an enough reason for studying the term in the light blue box. Okay, then now let's actually try to compute it. Our main tool is so-called HHA formula for McDonald polynomials by Catalan, Heyman, and Lohr. And here is the formula. For those who are familiar with HHA formula, we are using a slightly different convention as we are summing over inverses of permutations. For those who are not familiar with HHA formula, just ignore what I said. Anyway, to be more specific about the formula, f is the Gesell's fundamental quasi-symmetric function indexed by a composition. And stat lambda is the function that gives you some Qt monomial once you put a permutation of the appropriate size. And the only unclear thing in this page is the stat lambda, so I'll explain in a detail. First, for each cell, write the value q to the minus arm and t to the leg plus 1. I didn't write the values for the bottom row on purpose. You'll see why in the near future. And then we assign the number on each cell from above to below and from left to right order. Okay, so red letter has done that. We compute maj of W and inv of W. To compute maj of W, we look at each column and consider adjacent numbers. For example, we have 1 and 2. Then you look at the permutation W, and if 2 is left to 1, then you multiply with T, which is the value on the box with the number 1. And do the similar thing for the pair 2 and 4. Since there is no box below 4, the value on the box 4 is redundant. Now to compute inv of W for each box, look at boxes on the same line that are strictly right and boxes on the one line below that are strictly left. So for example, 2 and 3 and 3 and 4. And if 3, and look at the permutation, if 3 is left to 2, then multiply with Q and repeat this for every such pair. Finally, stat of W is the product of maj and inv. Note that we did not use the partition property of this diagram. So it means that once we are given any diagram with values on each box, we can compute stat D of the permutation in the same manner. In the example, this diagram is not in a partition shape, but we can basically compute inv and maj in exactly same way. So this is the way of computing maj and inv for this diagram. And for the example, if you give me a permutation 4, 3, 2, 1, and every pair is reversed, so maj of W is AB, and inv of W is Q to the cube. So the stat becomes ABQ cube cube. I'm saying this because later we'll deal with stat of D even if D is not a partition. Okay, then anyway, let's use HHA formula for the computation. And here is the table for 24 permutations and corresponding stat lambda and stat mu. Our goal is to compute this guy. to make problem simple, let's just assume that H tilde lambda is the sum of stat lambda, sum of the column here. And H tilde mu is the sum of stat mu. So the ideal situation we hope is that we have the ratio Q to the T or 1-to-1. If the ratio is Q to the T, then it will vanish once you plug in here. And if the ratio is 1-to-1, then it will come out as itself. But as you can see from the table, we are very far from the ideal situation. You see many permutation whose ratio is not Q to the T or 1-to-1. So this is bad. So we looked for other statistics that can replace the statistics in HHA formula. And our discovery of local exchange rule has made that successful. So basically, given a diagram with values on it, we focus on adjacent columns. If the values on the boxes satisfy a certain condition, then we can swap these two columns with a slight modification on the values. So we swap the columns, and the modification on the value occurred only in this box. And we proved the following identity. So this means that, so stat D and stat D prime, they are obviously different functions. But once we collect permutations that gives the same f in that collection, stat of D and stat D prime are equidistributed. For those who are familiar with additive polynomials, you will recognize that this is a linear relation among ribbon additive polynomials. Okay, let's do the example. The picture shows the diagram for stat lambda for the staircase partition in HHA formula. And to make our eyes comfortable, we split column by column. And the local exchange rule says that you can swap any adjacent columns with a slight modification in the value. First, let's swap the first two columns. And then let's swap the second and the third column. So local exchange rule says that we can compute McDonald's polynomial using stat prime or stat 2 prime instead of stat in usual HHA formula. And there will be up to stat 24 prime because basically we get every permutation of columns. Now let's get back to the example we failed. For lambda will not do anything. So stat prime, so there's a typo here. Here should be stat lambda. No. So yeah, this is stat prime lambda. And for stat mu, we'll use a local exchange rule and say this is stat prime lambda. And let's do the similar thing. Here's the table for stat prime lambda and stat prime mu. So as I said, ideal situation is the ratio Q to the T or 1-to-1. So it seems that the situation has been much better than before, but it's not perfect because in the middle, you see the T to the Q ratio, but it's possible to group the permutations properly. So the yellow permutations are those such that 4 is right to 2 and 3. And the light blue permutations are those such that 4 is left 2, 2 and 3. And among remaining permutations, green permutations have the ratio q to the t. So if you look at green one, the ratio is q to the t. And pink permutation have the ratio 1 to 1. If you look at pink one, then ratio are the same. So stats are the same. Moreover, after some calculation, the ratio of sum of stat prime lambda and stat prime mu on the yellow permutation is 1 to 1. And on the light blue permutations, the sum ratio becomes q to the t. It becomes, so it means that as a result of this one, we get sum of yellows and pinks. So our attempt has been successful. And the next question is, how do we classify the permutations that survived, yellow and pinks one? So we were able to combinatorially classify the yellows and pinks in general. And so far, we could not come up with a nice name for such permutations. So in this talk, we'll call them KL permutation, which is our initial sequence. Let's start. Given a permutation of length 2n, first add 0 on the left of the permutation and 2n plus 1 on the right of the permutation. After that, make directed arcs by connecting 2n from 2n to 2n plus 1 and from 2n minus 2 to 2n minus 1 and so on. Then for the smallest I such that ai and ai plus 1 is non-crossing, then look at if ai covers ai plus 1, in that case, we require ai to be in the reverse direction. And otherwise, we require ai to be in the forward direction. And there is also a condition for the degenerate case. Okay, then I'll do the example. If you give me the permutation 1, 4, 2, 3, then first add 0 and 5 on the left and right, and make directed arcs connecting 0, 1, 2, 3, and 4, 5. And compare the first two arcs, red one and blue one. These two are non-crossing. And the first arc covers the second one. So 4, 5 covers 2, 3. So in that case, we require the first arc to be in a reverse direction. But in this case, 4 and 5, it is in the forward direction. This permutation is not in KL permutation. If we had 5 and 4 instead of 4 and 5, this would be in KL permutation. And if you give me 1, 2, 3, 4, we do the same thing, add 0 on the left, add 5 on the right, and make directed arcs. And first two arcs, they are non-crossing, and there is no inclusion relation between these two arcs. And in that case, we require the first arc to be in forward direction. So 4, 5 is in forward direction. This permutation is in KLO. And if you give me the permutation 2, 4, 3, 1, we make directed arcs and you see many crossings. If you look at the first two arcs, red and blue, this is crossing. So you see blue and black one. These two are non-crossing. And blue one does not include the black one. So it goes to the case here. In that case, we require the first one to be in forward direction. So 2, 3 is in forward direction. So this permutation is in KLO permutation. And as you can expect, yellows and pinks that survived in a previous example are exactly KLO permutations in S4. Now our main result. There is some noise outside. Sorry. First, we gave an F expansion formula for this quotient in terms of KLO permutation description. And second, we proved that this is sure positive when lambda moved the cell on the first or the second row to make mu. We were able to write it positively in terms of LLT polynomials. So in this case, this gives the partial result for Butler's conjecture. And third, if we sum F for KLO permutation, it gives H211. So this implies that if we specialize Q equals T equals 1 to this one, then you will get H211. So more surprisingly, if we specialize Q equals T equals 1, then this guy does not depend on the shape of lambda and mu. And that was same for ordinary Macdonald polynomials. Okay, then now let's move on to QT Catalan number and Kraber's number in science fiction conjecture. Record a science fiction conjecture. So science fiction conjecture says that Frobenius characteristic of the intersection of K Garcia-Heyman module is a linear combination of K corresponding Macdonald polynomials. And here is a rather ugly explicit formula for that. And again, this formula is conjectural. And so far we dealt with the case for K equals 2 for the right-hand side, a linear combination of two Macdonald polynomials. Now we'll consider the case where K is bigger than 2. And here's the experimental data for Q equals T equals 1. The case K equals 1 is a single Macdonald polynomial, so this is a well-known result, H1111. And case K equals 2 is H211, and this follows from our result. And we don't know for K bigger than 3, I mean the proof. And so basically, if we look at Q equals T equals 1, then H expansion can be described very nicely in terms of some numbers, some combinatorial numbers. And the next question would be, what are those numbers? If you look at the numbers on the first column, 1, 1, 2, 5, 14, and 42. This is the number you know. They are called Catalan numbers. And the other numbers turned out to be Kraber's number. So Kraber's number for partition lambda is the number of ways of partitioning endpoints on a circle such that the convex hull of each block is disjoint. So if you give me the partition 2, 2, 2, 2, then we have 2 endpoints on the circle and we draw n lines such that there is no intersection. And this is exactly one of the descriptions for Catalan numbers. For the other example, picture on the left is the one way contributing to Kraber's of 3, 3, 2. As you can see, convex hull has no intersection. However, the picture on the right is not, as there is an intersection here. Let's get back to our data and at K equals 5. As you can see, every H coefficient is described very nicely in terms of Krabbe's numbers. So we conjecture that in general, linear combination of K-McDonald polynomials in science fiction conjecture at Q equals T is given by an H expansion with coefficients of Krabbe's numbers. I didn't write it here, but we have a recent progress. We know that the H coefficient of this guy is the number here. But we don't know if there is no other H with non-zero coefficients. And next, we proved that K-McDonald sums in science fiction conjecture has Schur coefficient as a QT Catalan number. If we take the coefficient of a certain Schur function as 2 to the k minus 1 and remaining part are all 1, then it becomes exactly k minus 1's QT Catalan number up to a QT monomial. And here is the formula for QT Catalan number appeared in today's talk by Professor Butler, combinatoric formula. And as an example, this is the screen capture of his talk, presenting QT Catalan number corresponding to the Catalan number 5. And our proof of this theorem highly relied on our local exchange rule that I showed you previously. Okay, so even if we have a proof, it was very mysterious to see QT Catalan numbers in science fiction conjecture story. QT Catalan number first appeared as the coefficient of S1111 in nebula of En. And this and the several combinatorial formulas were given and proved by these people. So to summarize, in science fiction conjecture story, if we do the Schur expansion of this guy, then the last non-zero Schur coefficient appears at here. The last means last by a dominance order. And if you look at the nebula of e to the k minus 1 and look at the last non-zero Schur coefficient, and they are both QT Catalan numbers. And recently we found a direct conjectural connection between these two. So if we apply En perp for the right size of n, which is size of lambda minus k, to the K-McDonald sums for the science fiction conjecture, then this becomes exactly nebula e to the k minus 1 up to a QT monomial. This conjecture explains the appearance of QT Catalan number. It is because if you apply En perp, then this Schur goes to here, and there is no other remaining non-zero Schur coefficients behind this. So this guy will only contribute to this one. And so far we have a proof for t equals 1, and we are trying to prove for the general case. And we also proved that if n is bigger than this right value, then the left-hand side is just 0. Okay, then I'll end with the future direction of research. First, we hope to give a positive, there should be positive, give a positive F expansion formula for these K-McDonald polynomial sums. And according to the previous conjecture, this would be harder than shuffle theorem. Because once you have a positive F expansion formula for this guy, then by applying En perp, assuming the previous conjecture is proved, then it will give an F expansion formula for nebula of AK minus 1, which is a shuffle theorem. And for the Butler's conjecture side, we have a F expansion formula for this guy. So to prove sure positivity, maybe we can apply dual equivalence graph technique. This is the future task. And for the last, Nabula Ek-1 has a very well-known corresponding module called diagonal harmonics, which is proved by Hyman. And this K-McDonald sum in science fiction conjecture has conjecturally nice SN module, which is the intersection of K-Garcia-Heyman module. And on the symmetric function side, we have a nice conjectural relation. They are related by E and perp. So maybe can we connect these two modules, representation theoretically or geometrically? Okay, I'll stop here. Thank you.
Thanks a lot for such a wonderful talk. Let's thank the speaker. Are there any questions?
Guess I have a question. That was really terrific stuff. So I'm wondering, at Q equal T equal 1, say, just very special case. I mean, what you have ultimately has to be sure positive, right? If science fiction is correct.
Right.
So can you take, for example, just that alternating sum of H's with Kreperos coefficients and prove that it's sure positive?
No, we don't know the proof for that.
And sort of another guess, I mean, that was a very interesting thing that you have about the image of E capital in perp. So E capital in perp, we have an interpretation of that at the level of modules, essentially applying an alternate in the first in variables. So what we have is that, assuming this whole thing works out, the parking representation is going to be the image of one of these alternates. Does that help you guess at all what the ungraded structure might be for the intersection of Garcia-Heyman modules?
Actually, I have no idea on that. So what I know is that so basically this guy is very hard to understand. So
yes,
if your idea can be helpful to understand this guy, it would be very great.
And I'm sorry to monopolize the time here, but of course, any symmetric function is characterized by its image under all E perp operators. Like if I were to do sort of not the, was it the E in minus K or E in plus K perp? I can't see if that's a minus or a plus. But if I were to do like 1 degree lower, do I get something that's kind of similar to Nabla EK minus 1? Is it sort of?
So actually we don't know. So the issue is that conjecturally, dimension of this guy is n factorial over K, conjecturally. And dimension of this guy is, what's that? K minus 1 to the K plus 1.
Or K to the K minus 2, I think, that thing.
Or maybe, yeah, K to the K minus 2. So it's very hard to find the natural sequence that goes from n factorial over K to the K minus 1, as K to the K minus 2.
Right.
So we have no idea on the side that happens in between these two.
Okay, thank you.
So I have a question. Can you go back 1 page to the previous future task?
This one?
So yeah, right there. So you say you know the F expansion for this quotient. So I believe it's an unsolved problem to find the monomial expansion for that. So it sounds like you may have the solution to that.
Sure. So once you have an F expansion formula, and if you know the function is symmetric function, then it is straightforward to write the monomial expansion.
So your F expansion is a positive F expansion?
Yeah, sure. Positive F expansion. Yes.
Okay, so you got the monomial. Okay, great. Yeah. And I had one other, not a question, a comment. Can you go to the slide on the Cruris again? Yeah. Yeah, there. Okay, so I was at this conference in Miami, the Walk Fest. It was about 10 years ago, and Vic Reiner was giving a talk on stuff related to this parking spaces paper with Brendan. And he had a Q version of the Cruris numbers, which came in there. And the Cruris decomposed the Neriana numbers. There's kind of a natural QT version of an Neriana number that arises from diagonal harmonics. And so Vic had posed the question, is there a QT version of the Cruris numbers, which when T is 1/Q would collapse to his Q Cruris?
So if we
Sounds like you just have Q and T equal 1 here to get the Cruris.
right. And
But
actually, we have a research for T, just T equals 1. So
okay.
just set T equals 1 and take the H coefficient of this guy, then we get some Q analog of Krabbe's number of this guy.
Well,
And
that might give good information to try and find a QT Cruris.
so unfortunately, if we set QT in general, then, and if we take the H coefficient of this guy, then there is no more positivity. If we set only T equals 1, then it has a positivity in terms of Q. But in general QT, there is no.
Did you by chance try T equal 1/Q?
No.
Okay.
Shall we try that now?
That's the setting of the parking spaces paper, so that's probably a little more hopeful.
Yeah, right. Yeah, the parking spaces is all the T equal 1/Q case of possibly some more general thing. Yeah.
Did you say T equal?
Oh, here we go. Ready to go here. Right.
Yeah. Huh? What? So this is the Schur expansion. And we want to substitute T equals Q to the inverse. Here is it.
Doesn't look all positive. Okay.
Okay, yeah.
So there was a comment in the chat that the Q Krabbe's number is different than the one defined by Reiner.
Mhm.
Any
right.
other questions? I have a question. So the new statistic like stat prime or double prime that you defined by doing this column changing, does that give another formula for McDonald polynomials or?
Sure, here.
Yep. So these are like two different statistics for McDonald polynomials, right?
Right. Yeah. Right. So basically, McDonald polynomial here can be written as stat prime and f.
And
stat 2 prime also works, and you'll have 24 such.
Okay. Any other questions? If there is none, then let's thank the speaker one more time for such a wonderful talk. I guess that's it for the conference. 이승진 교수님, can you take it over?
Sure, yeah. Thanks everybody for staying online. I mean, if you're not in Korea, then it's probably night. So thanks for everyone for participating and listening to the talk, and the first thanks to the all the speakers who gave great talks, and I guess